example. We have a solid shaft. It has the shear stress allowable 100 megapascal, and the elasticity, the modulus of elasticity is 39 GPa. The length is 2 meter. You can see the figure below. And then we have the twist. The allowable twist is 0.1 radian. If the torque applied in the shaft is 30 kilonewton meter, it's asking the diameter. Okay, so I think this is basically a direct question, so you just need to follow from the shear stress. You can get the shear stress allowable formula, and you get the diameter. But you can have two approach. Okay, first is from the shear stress. The second one is from the displacement. You can have these two answers, and as usual, we can compare these two answers, and then we can get the minimum from our computations. So first, we remember that we have the tau is equal T, and then we say this is R, right? And over, this is the inertia, right? And we also have another formulations using the displacement for the twist angle. That is T, L, and then G, and then inertia, right? So from both of these expressions, we can get the diameter. If you use the tau, you get the diameter. You can use the angle, you also get diameter. We have to answer from these two, and then you can take which one is the safest one. Okay, let me repeat it. I mentioned that next week, Friday, we're going to have a quiz on chapter 4. Okay, so probably only 2 questions, 1 hour class. Okay, in 1 hour class.
On slide exam.
Yeah, in class. Yeah. A Friday. Okay. Okay, now from this formula, from the tau allowable is, let me multiply T with the radius is the diameter over 2, and the inertia becomes pi, and then diameter with power of 4 divided by 32. So we can write directly the formula. If you want to compute the formula using this one, I think this is a very very helpful. If in terms of diameter, you can just directly write, if the shaft is solid, then you can write 16T over pi d cubes. Okay, that is for the tau. And then we can take the diameter from this part, so 16T over pi, the tau allowable, and then we take the cube root. Okay, so from here we can just compute 16, 30 kilo, so this is 3,000, 30,000. And then this is pi 100. This is for the allowable is 100 MPa, right? So this is, let me write this PA is Newton. So we get that D is 0.11518 meter. Okay. But this is not yet over, because the question is asking the minimum or the required diameter. Okay. So we need to check also the other formula. And basically we are just taking this and place all the subject inside. Perhaps we can write the d with the terms that d that came from the tau, and this one is d from the angle. Okay, so d angle is going to be 32. And now we are taking from the twisted angle. So if we input the numbers, we get that the diameter is 0.1119. So it's much less than the other diameter. So the requirement, so diameter required, then we take the one that is largest. Okay, that is the safest path to be taken. So diameter required is 116 millimeter. Okay, so next week we are going to have a quiz on chapter 4. Okay, next question. I think this is quite direct questions. Next questions, I think still also direct questions. This is about the power. So if you remember that this is the last part of our lecture in chapter 4, that we are discussing the power. So this is also direct questions. So first, let's read the question first. A solid circular shaft having a diameter 38 millimeter that rotates at the angular speed 100 rotation per minute. So of course, because there are some, it needs to have some conversion. So rotations per minute. So you need to equaling this to. So of course, this will take the radian over revolutions, and this will be 1 revolution is 2 pi, right? Okay, don't forget to convert that and convert the minutes to seconds. Okay, and it has the tau allowable 55. What is the maximum power? So it's directly asking the power. So remember the power. Okay, so the power max is the torque, right? Multiply with the speed, right? The angular speed. Okay, this is very basic in physics. Okay. And from this type of questions, perhaps the question is not only about this, can be also related to the previous problems. So for example, in the previous problems, usually you are asking to find the torque or find the angle, right? But then we add some additional, like an accessory. We add like questions like the power, or maybe it has the power, and then you need to define how much displacement for the angle. So you need to find the torque from the power, and then the angle, right? And then you find the displacement. It can be something like that. Okay. But I hope how you solve logically step by step. This is pretty similar to what we have in chapter 3. In chapter 3, remember, we have the force, right? We have the force, and then we have the elongations, right? We can think the force in chapter 4 is mostly the torque, right? And the displacement for the elongations, and now we have the displacement in angle. And how we are using the steps is pretty similar. So first, every time we have the diagrams, we draw the free body diagrams. We see how the internal stress, internal torque, right? And then after that, we can go for the compatibility equations, okay, to find the elongation or to relate the elongations with the force. Okay. It's pretty much the same like chapter 3, the steps. Okay. But the difference is we are having a torque instead of force, and we are having a twisted angle instead of the elongations, the displacement. Okay. So from this power here, the important point here is to find this T, right? The T is having, it's given diameter, right? And it's given the allowable shear stress. So perhaps we are going to take from this the allowable shear stress, right? So take this tau, and this will be T. And since it's already in the allowable, let me just write it and make this as the maximum torque that can be applied. T max, the radius over the inertia. Okay, it's always like that, right? And then we can rewrite this and makes the tau equal. So after some simplifications, this is 16 T, and as I mentioned, this is also very important. If you want to make sure it's helpful, then you can just write this in terms of diameter, right? So it's always 16 T over P D cubed. Okay. If you want to write directly, you can write this. And then T max, from this we get, we just take it to here. PD cube, right? And then divide by 16. So we get right to the P is pi, the D is 38, so 38 millimeter cube, and then it has 55 MPa, Newton over millimeter squared, divide by 16 and multiply with 100 RPM. RPM we need to define and convert, so per minute. So let me just take this 60 seconds. And then this is 2 pi radian per revolution, right? Or per rev. Just like 2. And then just calculate all these numbers, and then we get the power. Power is 6 point around this number, a kilowatt. So it's also pretty much direct questions. Okay, now the next one, we have this questions 454. We have a shaft. Okay, we have a shaft, and this will be a typical problem, and especially for your quiz, this type of questions will be, at least one of them will be like this. So you will have a shaft, and then you have some either displacement or torque, okay, and it has some certain conditions. So we have, at least we can see A, B, C, the point, and we see the shaft made up two components. Notice that the questions given you 1 and 2, so it's already giving you these informations. So first we can take the equilibrium first. Take the free body diagram for maybe we can see from the number 2 and the number 1. So it's asking first is the maximum shear stress. So to take the shear stress, we need to figure out how is the torque for each component. Okay. So we have 2 components, right? We have 2 components. It has some length for both of these components. So we can start maybe taking each one of them, and let's look on the internal side of the material. So the AB is solid, so let me write here. So AB is solid, and the BC is hollow, right? So the difference solid and hollow, you will see that it will be having a different inertia, right? Okay. So first, let's take the free body diagram. Let's start from number 2. So suppose that this hollow one and then let's cut in the middle like that. So the given torque, external torque is 3 kilonewton meter. So let's define here, right? That is 3 kilonewton meter. And to make it equilibrium, then we need to have, we make this as a center, and then we need to have that as our let's say T2, because this is the material 2, right? Material 2. So in equilibrium, the couple, the moment, or let me just write sigma moment need to be equal to 0. Let's say with respect to the axis, okay? Or let me just write this equals 0. So T2 is equal to this 3 kilonewton meter, right? Okay, and then we take the material 2 and then material 1, and then let's cut in the middle of material 1. Let's cut here. Okay, so this will be 3 kilonewton meter, and we have another external torque here, which is 8 kilo Newton meter. Okay, and then we can just make some assumptions. What kind of torque inside the material 1? You can actually suggest, because 8 and 3, you can see that it's larger for 8, right? So you need to have another segment like that for your equilibrium. So this is T1, and as you can see, the T1 is equal to 8 minus 3, right? Okay. Well, we could also take the T1 counter, and it will be the negative, which means that the direction is supposed to be the opposite, right? But let's say this is the possible one, right? the most logical one. And then based on this T1 and T2, we can take to this shear stress formula. Remember, this is tau T R divided by inertia. Or if you want to write in diameter directly, including the inertia, for solid, we get 16 d pi d cube. This is for solid. For hollow, then the difference is just in the diameter. This is for hollow. And then we can take the tau max for material 1. Okay, for material 1, this will be T1 multiply with, or let me just write to 16 T1, and then pi D1 cube. So 16 multiplied with the 5 kilonewton meter. And then divide pi, and this will be 50 millimeter, right? The D1. Cube. And after some conversion for the units, meter to millimeter, then we get this. This is going to be 203.72 MPa or Newton per millimeter squared. Same way for the hollow, we can input 16T2 pi so 3 kilonewton meter over, this is pi 50 millimeter 4, and then minus 20 millimeter with power of 4. And you will see that this is as we expect, that for the hollow, because of the inertia, it will have the smaller megapascal. They are typically the same material, right? But the difference is the shape. One is solid, one is hollow. Inertia is higher in solid, right? So this stress that so the question is asking the maximum shear stress in the shaft. It doesn't identify which one, right? But since we have the shear stress maximum on material 1 is higher because of the inertia, then we can say the tau max, we can take the tau max for the material 1, which is 203.72 MPa. So this is for question A, right? Question A. The question B is asking the displacement or the angle deformation. So the angle deformation, you see from here, see for a while here, let's just see for a while. So we see that we have the angle B and angle C, right? So we have two materials, 1 and 2. So if it's mentioned that there are two torque, right? So when we think on this angle for B, for example, for angle B, then it's only affecting the material one, right? Because the A is fixed, this is fixed, right? So we can directly say that the angle B is the same when you twist the material one also, right? But if you think from the angle C, you get that angle C will affecting number 2 and 1, right? So in the whole process, you see that the angle C is angle 2 plus angle 1. Okay? So geometry, that the angle C is angle 1 plus angle 2. Okay. So then the next step is we need to find the angle 1 and angle 2, which they are similar to the, or we say the steps is pretty the same with the elongations, right? So we get the twisted angle is T, L, G, and inertia, right? This is in comparison pretty similar to the elongation, which is half F, L, A, E, right? So you could directly compute using this formula, or you want to change this formula and make it more simplified, and you can have more good structure in your writings to help you to organize your solutions. You can write this as in F and T. Okay. This small f is L. So they are basically the same thing, but it's just helping you organize your structure. Okay. So in our case, that the angle 1 will be FT1, T1, right? While the F is L over G and then inertia. And the L for the number 1 is 800 millimeter. So 800 millimeter. This is 26 GPa, or 26,000 Newton per millimeter squared. And then multiply with the inertia. Inertia for solid is directly pi over 2. And then d over 2 power of 4. And we can write this is 32. So this is pi and 50 millimeter power of 4. Okay, you can compute this and we get that this is 50.1. This is for F1, sorry. Then we'll put this thing on the top here. Let me resize a little bit. And then writing the F2, same, and difference is the length is 32, 400 millimeter, divide same G differently inertia. And after some calculations, this will be equal to 25.7. I haven't checked the numbers if it's correct or not, but suppose that this is correct calculations. Okay, and then we can take that the angle B, as we mentioned before, is equal to angle 1, which is F1 multiplied with the T1. So we can multiply this 50.1 to the T1. T1 is 5 kilonewton meter. So it's around 0.25 radians. This is 0.25 radians. And the angle C is F1T1 plus F2T2. And this is around 0.17 radians. Oh, I forgot the unit. This is radian over kilonewton meter. So radian over kilonewton meter. Okay, I think maybe one more, but maybe not complete. But okay, wait. Okay, this is with power. You can write first the questions and try later on. I will provide with another practice to help you to prepare your quiz next week. Okay, so let me just explain a little bit how to solve this, and give you some hints and clue. So the solid steel shaft AD, as you see from the picture, it has some certain of length in between the shaft and diameter. It has 4 kilowatt power from the D. The shaft has diameter of 22 millimeter, supported by frictionless bearing at C, which means that we can ignore that. Rotates at the angular speed. So we get the angular speed 1500 RPM. And of course, this is we can convert to the radian. So divided by 60 seconds per minute. So this is around this. Okay, and then the maximum shear and maximum shear stress at A and gear at B, and then shear stress in the shaft between the two drive gears. So first is we need to determine from the angular speed. Remember that we can get from the power is torque multiplied with the angular speed. So for each one of them, we could get the torque. Okay, so it has different power, right? So at B it has 5.5. At D it has 4. So of course, because of this different power, then it will give you different torque, right? So let's say the TB becomes PB divided by the angular speed, and TD is PD divided by the angular speed. Okay, and then apply the diagram. So first we can see the CD. You can see the CD. Let me give you. This is the shaft. Let's say this is D, and this is supposed to be in between CD. So if this is the TD, then we are going to have, this is the T, let's say we name this as material 2. So let me write 2. Okay, and let's name the other part is 1. Okay, and now we can have this. So this is D, C, so this is 2. Okay, and then we have another one here. So this is TD, and this is, let's say, the TB, and to make it equilibrium we have T1 here. So we can get the equilibrium. Okay, and then later we can calculate the moment inertia and then calculate the tau. Okay, so after this we get to the tau equal T, R, and inertia. Okay, the torque you get from the power. Inertia you can calculate from the diameter, and you get the tau, okay, for each component, for CD and for BD. Okay, now I will upload these notes today, so you can check the notes and give you more exercise. Okay, and how to determine which way the torque will be? You can assume. Okay, first assume, but your assumptions need to be consistent throughout all the solutions. As long as in equilibrium, you can prove that it is equaling 0. The sum of the moment is equaling 0. Okay, and this is, we get the equilibrium here, and which means that this TD is equal to T2, and this TB means that from the power from the B here, and it means that it's in this C because there are no friction, so we can say that we can ignore that, and we can say that this is also rotate with the same power from the power shaft. Okay. And from here we get the equilibrium, so TB plus TD equal T1, okay, and then TD equal T2. From there, we get T1, we get T2, that is the one that we put here. So with each component, we get the shear stress. Okay. Okay, I think that's it for today's class.